In this video we will take a deeper dive into the math behind backpropagation, and in doing so get some intuition for what it means to backpropagate an error signal. What we have here is the gradient of our loss function. It contains the partial derivatives that we take with respect to the different weights. And since we have a lot of these, we need some efficient way to calculate them. Before we jump into that, let's quickly talk about sub and superscripts, because right now we differentiate the weights with the natural numbers 1, 2, 3, but that does not give us much information about where the weight is located. So instead we use a superscript to indicate in which layer the weight is located, and so instead of using 1, 2, 3, we will use an n, and the n stands for the last layer. So instead of going here in our neural network 1, 2, 3, we will do n minus 1, and n minus 2. And that makes sense because we will start at the back, and if we had natural numbers, then depending on the structure of the network, we would never really know where we are right now. Okay, back to our weight. Besides the superscript, we also have two subscripts, the I and j. These indicate which neurons the weight is connected to. Their order is a bit counterintuitive because the I refers to the right-hand side neuron. So for example, if we're considering this weight here, then the I refers to this neuron and the j would refer to this neuron here. So we have to remember that they are switched. Okay, now let's jump into our first partial derivative. And we will keep things general, so we are not considering, for example, a weight in the last layer connecting the first and second neuron or so, but we'll stay general with the I and j here. And so what we're here now asking is, how does the loss change with respect to a weight in the nth layer? And now our loss function here will be the mean squared error, and this is a nested function, so the loss function does not directly depend on our weight, but instead the weight affects the drive of our neuron, the drive affects the activation or the output, and the output is then somewhat directly affecting the loss, as we can see here. So if we split the derivative into these smaller parts here using the chain rule, we can then tackle them one by one. So let's start with this part here. How does the loss change with respect to the activation of our neuron? And for that we take the partial derivative of our loss function with respect to our activation. And now we are not considering the whole activation of the network, but just one output neuron, so the ith activation. So if we go back to our network, then we want to know how is the loss affected by this neuron here, or rather this output of our neuron. And we don't have to consider both activations, because weights in the last layer can only affect one neuron at a time, and thus only one output. Okay, so now deriving this with respect to our activation, since we're only interested in yi, we don't need every part of the sum, and so only the part where the yi is present remains, and the 1 divided by m will carry over from here. We can pull the 2 in front, so that's here, and then we have to again apply a chain rule here. So the inner derivative will be minus 1, since our yi has a minus here, so we'll multiply with minus 1. And we can write that a bit more concise by multiplying the 2 with our 1, so we have 2 divided by m. And we can also pull the minus 1 into our brackets. Okay, so that's the first part done. Now onto the second part. Here we ask, how does our activation change with respect to the drive? So, going back to our network, so how is this activation affected by the drive of this neuron? Of course, we don't specify that we're talking about y1 here. We could also ask, how is this activation affected by this drive? Both would be fine. And so this step is rather simple, because the activation of our neuron is just the activation function applied to our drive. And so what we have here then is just the derivative of our activation function. Okay, now onto the final part. How does our weight affect the drive? So how is this weight, for example, affecting this drive here? And so what our drive is that it is a sum over the previous activations, so of layer n minus 1, multiplied with the respective weights of our current layer. And we also had a bias. And now, just like before, not every part of this sum is relevant when we take the derivative. since we only have to consider the weight we're interested in. That means when our k here equals to our j here. And so you can see the sum goes away and only our weight ij remains. And now taking the derivative of this part with respect to our weight is rather simple, since we only multiply with the activation of the previous layer. And so the derivative is just this activation. Looking at our network, this just means that how much this weight here can affect this neuron depends on the activation of the previous neuron. To give you some quick numbers, imagine the activation here is 0, then the weight here has no way of influencing the drive of this neuron here. Okay, and then we can put this all together. And now we have to make one crucial observation. Because in this part here, you can see no j. There are only these i's here. And if you remember, the j refers to the neuron where our weight comes from. And that means we can reuse this part. And if we then plug in different activations, so different j's coming from different neurons, then we get the partial derivative with respect to the different weights. So if we set our j here equal to 1, then we take, for example, this activation here, multiply it with that part here, which depends on the I, so that is our fixed neuron here. That gives us the partial derivative with respect to that weight here. And if we switch to 2, then we consider this activation, we get the partial derivative with respect to this weight here. And finally, for 3, we take this activation here, and we get the partial derivative with respect to this weight. And so this part here, which we can reuse for multiple derivatives, we call the error signal. And it writes like this. And so since we note here the I, this will be the ith error signal. So the error signal of this neuron if we set I equal to 1. We could also be talking about, of course, about this error signal here. And we also have to note that we're talking about the nth layer. And so let's already write down this structure. So when we take the partial derivative of our loss function with respect to a weight ij in the nth layer, then we have this part here, which will be our error signal, that here, and then multiplied by this part, so the activation of the jth neuron from the previous layer. And this does now already look much simpler. And now, just as the word backpropagation suggests, we will take one step back. So we will go to the n-1th layer. And here things will start off very similar. So first we consider how the loss changes with respect to the activation. Then we consider how the activation changes with respect to the drive, and then so on. So compared to the last layer, this is very similar. But the difference is that we don't just consider one activation, but the whole activation of the network. And so we have this vector sign here, indicating that we are talking about y1 and y2 in our case here. And the reason we have to consider the whole activation is because a single weight here will affect this neuron, and this neuron here will affect, through these weights here, both outputs of our network. And since we're dealing with vectors here, the derivatives can look a bit complicated, but let's go through it. So taking the derivative of our loss function with respect to both activations just means that we take them separately, so with respect to first y1 and then with respect to y2. On this occasion you may have noticed already the hat, which I'm not saying every time, but the hat means that we're talking about an estimate. So this is not our true y, so the actual data, but we're just predicting a y, so the y hat with our network. Okay, so this vector encapsulates how the activations for our network affect our loss. And now next up we have here how the activation is affected by the drive. And here you already see two vector errors. And so in principle we would have to check each with each. So how is the first activation affected by the first drive? How is the first activation affected by the second drive? And how is the second activation affected by the first and then the second drive? And this is what we see in this matrix here. So 1 with 1, 1 with 2, 2 with 2, and so on. But since the second drive, so maybe let's zoom in on that. So the sum here stands for the drive, so the sum of the previous activations, and then the activation symbol here is then the activation. So drive activation. And this second drive here has no way of affecting our first activation, since the first output or activation is just the drive from here and then applies the activation function. And that means whenever we have here non-matching indices, so 1 and 2, they will just be 0. And so now if we look to our function and we are multiplying these here, then we can do some simple matrix multiplication. So that part goes in here, gives us that here, and this goes also in here and gives us that part. And if we now look at these parts here, so what we have here is the loss function, or how the loss function changes with respect to the drive. And also here, how does our loss function change with the drive now of the second neuron. And this notion of how does the drive affect the loss function we defined as the error signal. So going up here, we had this part here as the error signal, and that was just this part. So how is the loss affected by the drive? And now since we are not in the last layer anymore, we have to deal with 2 neurons, and so we have 2 error signals, or rather this vector here of error signals. Now of course, eventually how the weight affects the loss will not be a vector. So let's move on to the second part here in red, which will be a bit different since we now are 1 level deeper, or we moved 1 layer back. And so let's go down here. And this is now how does the drive change with respect to the activation. So let's look at our network again. This does look a bit messy now, but now we're talking about how are the drives of this layer here affected by the activation of some neuron in the previous layer. So right here we have the n-1. And even without looking at the calculations, the solution is very intuitive, because what's connecting the activation and the drives here are our weights. And so how much our drives are affected by the activation will be our weight vector. And now for the almost final step, we will consider how does the activation of our previous layer, so the layer that we are interested in, n-1, is affected by the drive. And this is again very simple, since the activation is just the activation function applied to the drive, and so the derivative is just the derivative of the activation function. And so now the very final step, and again we can see here for the first time again the j appearing. And here we are then finally interested in how is the drive affected by our weight. So going to our neural network, this would mean how is this drive here affected by these weights here. And this is just like the first time we did it. So it is the activation in these neurons that determines how much of a change these weights here cause on the drive of this neuron here. And so at the bottom here we have then the activation of the now previous layer, so n-2. Okay, so let's look back at our big equation for the second to last layer. We have this part here. This was the vector of error signals from the first layer that we considered. So these here are error signal I or 1 in the nth layer, and this is the error signal of the nth layer, also the second one. And what we're doing here is then we multiplied with the weights that connect to the neuron that we are considering. So we are in the n-1th layer. So if we consider this weight here, then we consider this neuron. And then we will multiply with these 2 weights here. So error signals of this layer here are multiplied with these 2 weights here. And that gives us then this big part here. And now again, as I teased just before, in this part there's no j, so the j only starts appearing here. And so this means we can again reuse this part for the different weights. The different weights being these here, so this one, and this one was the one we already considered. And so what this big term is here then again is an error signal, now of this neuron here. And we can actually see this looking at the equation here, since we defined the error term as how the loss function is affected by the drive of a certain neuron, so that is the error signal of the neuron. And here we see the loss function, and then here the drive in our n-1th layer. And so this way of backpropagating the error signal from one layer to the next is of course applicable for every layer. So if you look at this summary at the bottom here the error signal of the Lth, so a general layer, is defined as follows. If L is n, so the last layer, then we're dealing here with our loss function stuff. And then for every other layer, we multiply the error signal of the following layer, so the L+1th layer, with the weight of that layer, and also with the derivative of the activation function. And that gives us then the error signal of a neuron in our current layer.